Okay, thank you all for coming. The next talk by Lucy will be about the internals of the OS X kernel. She'll tell us a bit about how it works and that it apparently is Unix in there somewhere hidden after all. Please welcome Lucy.
Welcome to my talk inside the Mac OS X kernel. I chose the subtitle, Debunking Mac OS Myths, because there are quite a few buzzwords associated with Mac OS X that are not entirely true. Like, is it Unix or Mach or whatever? Like, for example, Paul Thurrott writes, on the Mac, this kernel is called Mach, and it's based on rock-solid Unix technology. Well, let's talk about that. And a company named Apple states, with its stable open source core based on FreeBSD 5. It is stable, right? And yet another Apple quote, Unix-based. The question is, if it is Unix, why haven't they been sued by the SCO? Mr. Jobs must know better, right? He says, Leopard is 64-bit top to bottom. I guess it all depends on how you define bottom. And this is my favorite. Obsolete microkernel dooms Mac OS X to lag Linux in performance. This article goes into length pointing out why microkernels are inherently slower. Microkernel? Microkernel? So far with the buzzwords. To clarify them, we'll first have a brief look at the history of the operating system. In 1984, Apple introduced Macintosh. It ran on a machine with 128K of RAM, a 68K CPU, and it ran off floppies, and it did not support multitasking. 10 years later, System 7 was now running on PowerPC, and it finally supported multitasking. But it was not really PowerPC native, because large chunks were still emulated 68K code. And multitasking has only been retrofit, and it was only cooperative. So there was still no memory protection. From an architectural perspective, System 7 couldn't even keep up with Windows 95. The same year, Apple decided to do it like Microsoft had done it with Windows NT. They decided to write a new operating system from scratch, but with the same API, so that the old applications could run unmodified. This project was called Copeland, and it looked like that. But it slipped and slipped and slipped, and it finally got cancelled in 1996, because at that time, Apple had realized that this project was going nowhere and that it would probably never be released. They had handed out a few previews to developers, but there was no consumer product. So, Apple looked for an operating system to buy. There's something not really working. Oh, sorry. So Apple looked, like I said, for an operating system to buy. And they had a closer look at two operating systems of the time. One was Steve Jobs' next step. Steve Jobs was the former head of Macintosh development, and he had left Apple in 1985, and then he founded the company Next. Here's a screenshot of Next step from around 1995. Option number 2 was BOS. The company B was founded by Jobs' successor to Macintosh development. He was called Jean-Louis Gasset. And Jean-Louis Gasset had also left Apple in 1991. And here's a screenshot of BOS, also from 1995. Apple talked to Gasset about buying BOS, but ultimately they decided on buying Next. Next step became the Next operating system, and Steve Jobs was the new CEO. So, what about Next? The mission of the company was not to compete with Apple, but to design more high-end computers that were targeted at the education market with its own operating system that would fit well into the typical university infrastructure. One interesting fact about NeXTSTEP is that Tim Berners-Lee developed the first web browser on a NeXT machine. And probably more important, the level editor for Doom was developed on NeXTSTEP. But let's look at the history of the NeXTSTEP operating system. Like I just said, NeXT was founded in 1985, and NeXTSTEP 1 was quite a powerful operating system with a Unix base. It supported preemptive multitasking, had memory protection, a display PostScript GUI, and it ran on 68K hardware. So it was definitely more advanced than the Macintosh released 5 years earlier. One other significant release was 3.1, because NeXT opened it to other CPU architectures, i386, PA-RISC, and SPARC, SunSPARC. When Apple acquired NeXTSTEP in 1996, it was ported to PowerPC, and they added some core classic Mac OS technologies like the HFS file system, QuickTime, Toolbox, which is the GUI library, iTunes, and sadly, Finder. They also added a VMware-like virtual machine monitor called Classic to run the old Mac OS and its applications on the new operating system. But they didn't release a product, just a preview for developers under the name Rhapsody. Mac OS X, the desktop Mac OS X, was not released until 2001. In 2005, the i386 port was revived with the introduction of the Intel-based Macs. The final version was released in 2006, but they had handed out the developer's preview in 2005. Well, let's look at the architecture of Mac OS X, and we'll start with the kernel, which is called X and U. X and U stands for X is not Unix. And so much for Mac OS X being Unix. But more on this later. The kernel consists of three major parts that are Mach, BSD, and the I/O kit. Mach was originally a research project at Carnegie Mellon University, the CMU, started in 1985. Mach is the microkernel project. So let's first look at the difference between a monolithic kernel and a microkernel. On traditional monolithic kernels like Unix, BSD, Linux, other components run in kernel mode, like the file system framework, security components, user mode interface, the network stack, and device drivers. And besides those things, the parts that really need to be in kernel mode also run in kernel mode. On a microkernel, the kernel user boundary is moved down, so only the really necessary parts run in kernel mode. Again, the scheduler, memory manager, the interprocess communication, and low-level hardware access. Components like the file system or networking are each implemented in their own address spaces in user mode. Microkernels have the advantage that a crash in a driver, some file system logic, or a network protocol does not have to necessarily bring the system down, the whole system. In many cases, the faulty component can just be restarted, just like a user application. A similar advantage applies to the security vulnerabilities in a component. If malicious code runs in the context of a network driver, it doesn't have full control over the system. And in addition, dividing the kernel into components makes it more maintainable. Because it was simpler, CMU decided not to rewrite their own set of user mode components. So they decided to reuse BSD kernel code base. Here's BSD. And they ripped out the components that were already implemented by Mach and ran the rest in user space as a single server. On the next two slides, I'll demonstrate how communication between a user's process and the BSD server works on a microkernel. For comparison, Let's first look on a monolithic kernel. Here's a task in user mode that makes a system call to, for example, write. And this is not much more than a function call because it is a kernel user switch, but the address space stays the same. And the kernel function does its job and returns to the user in the same way. On a microkernel, the kernel does not have an implementation for write. Write is implemented in the BSD server. So the program has to send a message with a request to the BSD server using IPC. It calls the IPC function in the kernel. The kernel then switches address spaces to the BSD server. The message gets delivered to the BSD server. The BSD server performs the function, returns to the kernel, and the kernel switches address spaces again and returns to the user. The problem with this design is that address space switches invalidate the TLB, the translation leukocyte buffer, which is the cache for virtual memory mapping. And consequently, virtual to address space lookups become lower after a switch until the TLB is repopulated. So, all in all, this leads to performance problems. Because of this performance loss, the CMU decided to move the kernel user boundary up, so the BSD and Mach are both run in kernel mode. This is referred to as collocation. Consequently, Mac OS X does not have a microkernel design, because since next step 1, the combination of Mach, which is the actual microkernel, and BSD run in kernel mode. The question you might ask now is, isn't this just like a monolithic kernel? Well, it is. But this combination has its advantages too. Like, there's a clean separation of machine management and BSD compatibility parts of the kernel. It makes the kernel more tidy and well abstracted. And Mach had many improvements too, especially over the BSD equivalents of its components. For example, the memory management of Mach is better than the BSD one, until BSD copied it then. Talking about Mach, let's talk about the jobs or tasks of the Mach code. On the left side of the picture, you see physical address space, and Mach manages mapping from virtual address spaces to physical addresses. These address spaces are called tasks, and Mach does the memory management. These tasks are policy-free, which means address spaces are just a set of pages. There's no user ID, no working directory, no command line or associated terminal, or environment variables, or practically all the other fields that you get by typing PS on a Unix-like system. Mach allows one or more threads per task, and it does scheduling. Mach also, my computer is slow, sorry. Mach also sends messages between tasks. It does IPC. Neither the memory management nor scheduling are really worth having a look at, but IPC is a distinguishing feature to other kernels. So we talk about Mach IPC. A task can have any number of ports, and there are sender and receiver ports. The blue ones are sender ports, and the red ones are receiver ports. Mach messages get sent asynchronously, so the recipient can be busy and doesn't have to accept the message immediately, because the kernel buffers them, which means it puts them into a queue. Puts them into a queue, and here's another message, sent and put into the queue. If the recipient then wants to pick up a message, the oldest one gets picked up first, and the next one. The most common use case for IPC on a microkernel is the RPC, which is the remote procedure call, a function call across address spaces. For example, a call from an application to the BSD server. Unfortunately, it's pretty complicated to use Mach IPC for RPC. And that's what the Mach interface generator, or short MIG, is for. MIG simplifies RPC. For example, if main wants to call func, which is in another address space, MIG generates func in the first task, which looks exactly like func in the second task, but it just combines the arguments into a message and sends it to the other task. The other task then receives the message, decodes it, and calls the local func. The return value will be sent in an analog way. So, effectively, a function in task 1 just call a function in task 2. The blue code is generated by MIG from an interface definition file. Now, let's look at how BSD interacts with Mach. Like we said, Mach consists of the components memory manager, scheduler, and the interrupt or execution handler for low-level hardware management. These components use the concepts of Mach task, Mach thread, Mach exceptions, and Mach message. Then, BSD sits right on top of these concepts and extends a Mach task into a BSD process by adding context like the command line, a working directory, and so on, as well as extending a Mach thread into a POSIX thread, and it also converts Mach exceptions into BSD signals. BSD also adds extra components like the virtual file system, BSD sockets implementation, and the /dev infrastructure. On top of all this, there's a syscall interface. It exports the syscall interface, exports standard Unix syscall functions like open and fork to userland. Oh, sorry. What is wrong with that? Is there okay. Mach message API gets exported to user and directory. So there are basically two syscall interfaces, one to BSD and one to Mach. The syscall handler distinguishes between those by looking at the syscall number. And positive numbers get routed to BSD because these numbers are compatible with the standard syscall numbering of BSD, and negative numbers call into the Mach APIs. Applications should never make syscalls directly, but always go through libc, because Apple doesn't guarantee a stable syscall interface. And this is the reason why Mac OS X does not allow static binaries, that is, executables that contain a copy of libc in their binary. Such a static binary might not work on later versions of Mac OS if the syscall interfaces change, of course. The third component of Axon uses the I/O kit, which is the driver infrastructure. I'll first demonstrate how driver development traditionally works on systems like Windows or Linux. If you want to create a new driver, you usually take the closest match, you duplicate the C file, and you make the respective changes to the new file. This creates a lot of duplicate code, and it will always duplicate the bugs too. And it makes overall maintainability harder. A simple solution, or rather workaround for this, is to unify the C files and mark the differences with ifdef or if-tests at runtime. Obviously, neither solution is very readable, and runtime ifs even have a performance impact. So this is how the I/O kit does it. It solves the problem by using object orientation and a subset of C++ programming language. A generic driver is then used as a base class, and a more specific driver inherits all the code from this class and overrides all the functions that need a different implementation. The I/O kit offers many more and powerful modern features, but I'm not a driver person, so let's move on to the kexts. IOKit drivers are a special form of kexts, which are kernel extensions. A kext is practically anything that loads into the kernel at runtime. It's just like the Linux kernel modules. And kexts can also contain a file system driver or network protocols, or just provide random functionality if the kernel provides the necessary interface to hook into. This is a picture of some kexts that are stored in system library extensions, like, for example, as you can see, the Apple iSight kext, or Apple ABD keyboard kext, or Apple AirPod kext, and so on. This is the MS-DOS file system kext, which is the FAT file system driver. As you can see, a kext isn't just a simple file, but it's actually a directory that contains, next to the actual binary, a few other files, like, for example, the info plist. This file, just like the others, contains meta information about the kext, like the versions of the application binary interface of the XNU components that it requires. This example requires at least 8 of BSD, version 8 of BSD, Mach, and unsupported, and version 9 of libkern. Libkern is another small component of XNU that provides various utility functions like C++ base objects, data types, or atomic functions. And unsupported puts together all functions for which Apple doesn't guarantee compatibility in future versions of Mac OS. That's why it's called unsupported. Now, let's move on to booting. Booting of Mac OS is very different to booting a PC. So let's look at that first. On a PC, booting works through the firmware called BIOS, the basic input-output system, which is an ancient 16K bit firmware that can only address 1 meg of memory, which you can see on the right side. The only thing that BIOS does is read the first sector, the master boot record, into the lower 30K of RAM and jumps to it. So the BIOS does not know about partitions, partition types, or file systems. So the boot sector is completely on its own to find partitions and the files inside the file system that are required for booting. Booting on Mac is quite different. The Intel Mac firmware is called EFI, the Extensible Firmware Interface, whereas PowerPC-based Macs used Open Firmware. It's a different system, but it has basically the same set of features. In contrast to BIOS, EFI is 32-bit code, and it understands the EFI partitioning scheme called GPT. It also understands the old Apple Partition Mac, APM, used on PowerPC Macs, and it can read HFS. It detects which partitions are bootable by actually looking into the file system. If you hold down the Option key while turning on a Mac, EFI will present a boot picker, which shows all bootable partitions connected to the machine. EFI then reads the bootloader file from the selected boot file system and executes it. The driver kernel extensions, the kext, like I just said, are loaded by going through all the objects in system library extensions, and they're matched against the detected hardware. In case neither the kernel nor the hardware nor the set of drivers on disk has changed since the last boot, the kernel cache gets loaded instead, which is the kernel and a set of necessary kexts that were pre-linked into a flat image. It's also interesting to know that the kernel file is called microkernel, but of course it's XNU and not Mach. If you look at the file type of an executable like this kernel file or a library, you will see that instead of virtually every other Unix-like system, Mac OS X does not use ELF, but Mach O. For example, the lib system is a 4-way universal Mach O file, which means it contains code for all 4 supported architectures. One advantage of that is that no separate directories for 32 and 64-bit libraries are needed, as on Linux or on Windows. And this goes even further. Every single file, every single binary on a Leopard disk, even the kernel, runs on PowerPC and Intel. So the same hard disk can be used to boot computers with totally incompatible CPU architectures. The kernel function, grade binary, is responsible for choosing the most suitable binary image in one Mach O file. So if on a 64-bit system there's a 32-bit and a 64-bit part in the file, it'll choose 64-bit, of course. And on an Intel system, it will choose Intel over PowerPC. But if there's only a PowerPC image on an Intel system, it will choose this one and invoke Rosetta. Rosetta is a compatibility solution which is licensed by Transitive that allows running PowerPC code on Intel hardware. There are 2 basic ways of constructing something like Rosetta, and I'll first show you how it's not done. In kernel mode, we have X and U sitting on top of the hardware, and libsystem sits right on top of the kernel interface, and on top of that, there are several libraries. Rosetta could use all the native i386 versions of these libraries, sit in the address space of the PowerPC application, and translate all its instructions on the fly, and interface the application to the library. A problem is that PowerPC is big endian, while Intel is little endian. So Rosetta would have to translate all the data that is passed between the emulated code and the native library. So it's not done like that, because the interface between an application and the hundreds of libraries that it might probably use is very broad. And Rosetta would have to know about all the data structures that are passed between these interfaces. Instead, it loads and translates the application and all the libraries that are needed, that are required by the application. It loads it down to libsystem. So it only needs to do byte swapping between libsystem and the kernel interface, which consists of not more than a few hundred calls in total. So it's a lot easier to get right. The downside of this, of course, is it's slower. Like, for example, if a PowerPC application uses the QuickTime library, the movie decoder will run in a translated fashion, although it will be available natively on the system. You can make your own experiments and run the PowerPC version of a universal binary explicitly by running user libexec OAH translate, and you'll see it's slower. Talking about Intel and PowerPC, let's look at the different architectures NextStep or Mac OS X have been available for. Like I said, they started off as a 68K operating system, and it was ported to i386 and PA RISC and Spark, and ported to PowerPC by Apple. And although i386 version has always existed, and it was actually released as a part of Darwin, it hasn't been part of a consumer product until 2006 with the introduction of the Intel Macs. So no i386 NextStep or Mac OS X was available between 1997 and 2006, just the open source Darwin pods, not a product. The Intel kernel of Mac OS X has 2 interesting features that distinguishes it from other operating systems. One of them is the split of virtual address space into the user and kernel part. On most other operating systems, like Linux, user mode occupies the lower 3 gig and kernel mode the top 1 gig. So when the kernel switches between tasks, it replaces the lower 3 gig with pages of another user. This is called the 3-1 switch. Instead, Mac OS X on Intel uses a 4-4 switch. So, both the kernel and the user get 4 gig each. Consequently, only either can be mapped at a time. And a tiny switcher that is constantly mapped into the very top of the address space replaces the complete page table to switch between the kernel and the user address space. This design has been chosen to be able to map more devices, including large graphic cards, into the kernel address space, and it has an additional advantage. It provides user tasks with 4 instead of 3 gig. The downside of that is that 2 address space switches that are necessary for a syscall, including the TLB flushes, aren't that great for performance, again. Another property of the OS X kernel that isn't done in any other operating system is how support for 64-bit is implemented. While XNU supports 64-bit user applications in the respective 64-bit address space, the kernel itself is 32-bit code, and it resides in the lower 4 gig of the huge 64-bit address space. The picture is not really accurate, but it's simplified to get my point across. It is supported by a tiny amount of 64-bit code that sits at the top of the address space, which manages interrupts and switches between tasks and threads. The illustrates a switch from the kernel to a 32-bit user, back to the kernel, then to a 64-bit user. This is probably not the cleanest design, because the kernel cannot directly access the native address range and cannot make use of the extended set of wider registers that are available to 64-bit code. An advantage is that a single kernel image can be used on both 32-bit and 64-bit machines. Plus, the porting effort was minimized. And existing 32-bit drivers can be used unmodified. And besides PowerPC and i386, ARM is another architecture that XNU runs on since the iPhone's release in 2007. Although there is a big hype around the iPhone, there's not much special about its version of Mac OS. It's just another port to another architecture. But the iPhone uses a custom bootloader, and it does not support real texts. It always uses a kernel cache because it doesn't support extra hardware. What's sad about the ARM port is that the changes required for this architecture are not open source. But large parts of Mac OS X are. Apple calls this open source parts of OS X Darwin. Darwin includes the kernel, many drivers, Unix text mode userland, and many libraries. So Darwin is everything but the GUI and its support libraries. They release a new source drop with every minor release of macOS, like 10.5.0 or 10.5.1. This is a part of the list of the packages that can be downloaded from Apple's open source website. You'll notice that some of the packages are Apple's own code, like XNU, and some are modified versions of common open source software, like zip, Perl, curl, and so on. Apple Source is licensed under the Apple Public Source License, the APSL, which is a BSD-style license. And it's compatible with Sun's DDL, which allows the integration of Sun code, like dtrace and ZFS. But Darwin is not a typical open source project. There used to be the Open Darwin community that worked on the Darwin source, but interest in this has faded, and today basically only Apple is working on the OS X source. The picture shows the lovely Darwin mascot, Huxley the platypus. But although there is no hobbyist community working on the source, it doesn't mean being open source doesn't serve a purpose. It does. The source is useful to CAX developers for debugging and governmental and research institutions and third-party vendors. They often work on modified versions of Mac OS. For example, the mandatory access control framework, which is integrated into Leopard, have been developed by a third party. Now that we've talked about some major distinguishing properties of macOS, let me tell you my 8 favorite distinguishing features. Number 8 is dtrace from Sun. So it isn't a unique Mac OS feature. It was later ported to Apple, which is no problem because, like I just said, the CDDL is compatible with the APSL. Nevertheless, dtrace is a very useful kernel feature. It is a framework for getting statistics data from the kernel with near zero speed impact. On a running system, dtrace can just rewrite some kernel code to put code in there that does extra logging. And when the measurements are finished, the code can be removed again. Traditionally, the user either had to compile a special kernel with logging code in it, or always have this logging code enabled and suffer from the performance hit. Dtrace is very useful to get information about, for example, which syscalls does an application and how often, the number of memory allocations and frees for a driver. Those two are pretty obvious cases. A very obscure case is how often does grade binary decide to run the 64-bit part of an executable, for example. Number 7, the kernel cache. Linux has a similar system with its initial RAM disks, the init.rd, which are mounted before the actual root file system. And they contain a script that loads a set of drivers that also comes on this RAM disk. But it's just not as nice. Because the kernel first boots from a tiny installation in the RAM disk, including a shell, because you have to execute the scripts, and throws away the RAM disk and then boots the real root. This is a hack because neither the kernel nor the bootloader really support the concept of a kernel cache. On Mac, it is a supported concept, and the bootloader just loads a single file. Number 6 is the separation between Mach, BSD, and the I/O kit. Unix was the big mess, as Tenenbaum called it, because every function inside the kernel could call every other function, and there was no strict layering. BSD and Linux copied this design. And although Mac OS does not have the advantages of a microkernel, the kernel is still strictly divided into 3 distinct parts. The I/O kit, for example, forms its complete own world, and it only interacts with Mach through a narrow and strict interface. Number 5 is the POSIX conformance. Mac OS X was enhanced to pass the POSIX conformance test from the open group. So in contrast to Linux, it may carry the Unix trademark, but only since Leopard. Governmental customers want that, and fine by me. Number 4, the Mach message API. All Unix-like systems have the standard Unix means of IPC, like sockets, signals, and shared memory, but none of them is as powerful as Mach messaging, because Mach messaging handles security queuing and, if necessary, even data conversion. But it is not a feature provided by some library, but it's handled directly by the kernel, unlike Corba and Linux. Number 3 is the I/O kit. The I/O kit is a modern object-oriented driver infrastructure that supports inheritance, driver stacking. For example, CD-ROM sits on top of IDE, which sits on top of PCI, and it supports automatic matching and loading. Number 2 is the stable CAXT ABI. On Linux, a driver module typically even doesn't load into the next revision of the kernel. While this has the advantage that Linux can change the driver API at any time, it makes it extremely hard for third parties to provide the user with drivers. On Mac OS, the driver API is typically compatible with several major releases, so that you can, a lot like on Windows, just download a driver binary from the hardware vendor. And number 1, which is my personal favorite, the desktop OS X runs on 2 completely different hardware architectures, or 4 if you also count the 64-bit versions. Nevertheless, it comes on one single install DVD, and an installed system can boot on any of the supported architectures. And third-party applications that you download also run automatically on all systems. This is unlike Linux, BSD, and BSD, which require a different installer or installer CD, even for 32 and 64-bit versions of Intel, and they don't allow a 64-bit machine to boot, a 64-bit installation to boot on a 32-bit machine. To conclude my talk, let's revisit the buzzwords again and clarify their relation to Mac OS. Mach. The Mac OS X kernel is not Mach. The Mac OS X kernel is X and U. X and U consists of Mach, BSD, and the I/O kit. The OS X kernel is not a microkernel. The Mach codebase can be used as a microkernel. X and U itself is a monolithic kernel. BSD and most drivers are in kernel mode. FreeBSD kernel. The Mac OS X kernel is not based on the FreeBSD kernel. X and U contains some FreeBSD code. X and U is not written in C++. The I/O kit is written in embedded C++. Mach and BSD are written in C. The Mac OS X kernel is not 64-bit. It supports 64-bit userland applications. The kernel code is 32-bit with tiny 64-bit parts for user support. The Mac OS X kernel, most of the Unix bits are open source, but there is no live repository. Some code is missing, but it can be compiled into a working system. Mac OS X is Unix, but only since Leopard, because it passed the POSIX conformance test, and it now may use the Unix trademark. But it does not contain AT&T Unix code. But Mac OS X is awesome. Thank you very much.
Okay, thank you all for coming. The next talk by Lucy will be about the internals of the OS X kernel. She'll tell us a bit about how it works and that it apparently is Unix in there somewhere hidden after all. Please welcome Lucy.
Welcome to my talk inside the Mac OS X kernel. I chose the subtitle, Debunking Mac OS Myths, because there are quite a few buzzwords associated with Mac OS X that are not entirely true. Like, is it Unix or Mach or whatever? Like, for example, Paul Thurrott writes, on the Mac, this kernel is called Mach, and it's based on rock-solid Unix technology. Well, let's talk about that. And a company named Apple states, with its stable open source core based on FreeBSD 5. It is stable, right? And yet another Apple quote, Unix-based. The question is, if it is Unix, why haven't they been sued by the SCO? Mr. Jobs must know better, right? He says, Leopard is 64-bit top to bottom. I guess it all depends on how you define bottom. And this is my favorite. Obsolete microkernel dooms Mac OS X to lag Linux in performance. This article goes, there's something not really working. Oh, sorry. So Apple looked, like I said, for an operating system to buy. And they had a closer look at two operating systems of the time. One was Steve Jobs' Next Step. Steve Jobs was the former head of Macintosh development, and he had left Apple in 1985, and then he founded the company Next. Here's a screenshot of Next Step from around 1995. Option number 2 was BOS. The company B was founded by Jobs' successor to Macintosh development. He was called Jean-Louis Gasset. And Jean-Louis Gasset had also left Apple in 1991. And here's a screenshot. So there was still no memory protection. From an architectural perspective, System 7 couldn't even keep up with Windows 95. The same year, Apple decided to do it like Microsoft had done it with Windows NT. They decided to write a new operating system from scratch, but with the same API, so that the old applications could run unmodified. This project was called Copeland, and it looked like that. But it slipped and slipped and slipped, and it finally got cancelled in 1996, because at that time, Apple had realized that this project was going nowhere and that it would probably never be released. They had handed out a few previews to developers, but there was no consumer product. So, Apple looked for an operating system to buy, into a lens pointing out why microkernels are inherently slower. Microkernel? Microkernel? So far with the buzzwords. To clarify them, we'll first have a brief look at the history of the operating system. In 1984, Apple introduced Macintosh. It ran on a machine with 128K of RAM, a 68K CPU, and it ran off floppies, and it did not support multitasking. 10 years later, System 7 was now running on PowerPC, and it finally supported multitasking. But it was not really PowerPC native, because large chunks were still emulated 68K code. And multitasking has only been retrofit, and it was only cooperative.